experimental investigation of a four-bladed vertical axis wind turbine using plastic blades for power generation. This project is presented by MD Shamsul Arifin, MD Ashikuzuman Nairab, MD Hazabul Hassan, Mir MD Shanawaz, and MD Mahadi Hassan, all pursuing their Bachelor of Science in Mechanical Engineering at the World University of Bangladesh. The project was conducted under the expert supervision of MD Shariful Islam. Wind energy is a vital and growing resource worldwide. However, in Bangladesh, its practical application remains limited due to consistently low average wind speeds across much of the country. These low wind speeds typically result in low power output from traditional turbine designs. Furthermore, unsuitable turbine designs and inherent system losses often combine to significantly reduce the overall efficiency of wind power systems in these regions. The primary objectives of our research are threefold. First, we aim to design and build a functional, small-scale four-bladed vertical axis wind turbine specifically utilizing lightweight plastic blades. Second, we intend to accurately measure the resulting voltage and power output under various conditions. Finally, we seek to study the specific effects of our blade design on the turbine's overall performance and efficiency. Our literature review encompassed several key studies on small-scale vertical axis wind turbine design, including notable work by Rashid and colleagues in 2025, as well as research by Nandi and Bukala in 2016. Through this review, we identified a significant research gap. There are currently very few studies focusing on the performance of four-bladed plastic turbines specifically optimized for low wind speed conditions. Moving to our methodology, let's look at the top view of our design. This image shows the top view of the four-bladed turbine, featuring four curved plastic blades arranged symmetrically around the central hub. This symmetrical arrangement is critical for ensuring the turbine can capture wind effectively from any direction, which is a key advantage of the vertical axis design. Our tools included these plastic sheets, a DC motor, a central shaft, and a sturdy stand for testing. In this side view, we can clearly see how the plastic blade connects to the DC motor through the central shaft. This assembly is the heart of the turbine's mechanical system. During our procedure, we built this turbine, placed it in front of a controlled fan to simulate wind, and used a multimeter and LED load to measure the electrical output while systematically changing variables to compare results. The working principle is best understood through this main overview diagram. It illustrates the complete system, starting with the curved turbine blade design that captures the wind. This rotation is transferred to the central rotor and alternator, which converts the mechanical energy into electricity. The diagram also shows the circuit diagram for power management and the energy storage system. Interestingly, it highlights a traffic airflow collector concept, where the turbine could be placed near roads to capture the wind generated by passing vehicles, leading to the final power output. Here we see the fully assembled four-bladed vertical axis wind turbine model. This complete prototype integrates all the components we've discussed into a single functional unit. The use of plastic for the blades makes the entire structure lightweight and cost-effective, which were key considerations in our design process for low-wind applications. Regarding our expected results, we anticipate recording detailed voltage, current, and power measurements across a range of varying wind speeds. These data points will allow us to map the turbine's performance curve and demonstrate its practical ability to generate usable power even when wind speeds are relatively low, validating our design objectives. In our discussion, we highlight that the primary advantages of this VAWT design are its low cost and simple construction, which make it a viable option for small-scale power generation. However, we must also address certain limitations, such as the inherently low power output of small turbines and potential concerns regarding the long-term durability of plastic blades when exposed to the elements and continuous mechanical stress. To conclude, our experimental investigation has successfully resulted in the design and construction of a functional four-bladed vertical axis wind turbine. We have demonstrated the feasibility of using lightweight plastic blades for power generation, particularly in environments characterized by low wind speeds, providing a promising path for localized renewable energy solutions. Looking ahead, the future scope for this project is extensive. We plan to investigate different blade materials to further optimize performance and durability. Additionally, we aim to refine the blade angle for maximum efficiency, explore scaling up the design for higher power requirements, and integrate more sophisticated battery storage systems to ensure a steady and reliable power supply. This project is firmly grounded in academic research, with our findings supported by key references in the fields of wind energy and turbine engineering. These references provide the necessary theoretical framework and comparative data to validate our experimental results and design choices. Thank you for watching.